Okay, welcome back. Do I just start? Yeah, I can just start? Okay. Good. Maybe before we begin, since I wasn't here on Monday, I didn't get to get an introduction of every one of you, so I'm not sure if you're familiar with this or that and whatnot. So, who are you familiar with gradient flows? Give me a show of hands. Wow. Who are you familiar with gradient structures? Okay, very good. So this lecture series is about gradient structures, which is very, very related to gradient flows, but different in the sense that when I say something is a gradient flow, this is not very precise. So by saying that something is a gradient structure and giving sense to this gradient structure, suddenly the gradient flow is manifested via this gradient structure. So I'll try to clarify what I mean in a little bit. But before we begin, I want to make maybe a prelude to this lecture series, just to give you a motivation of why I'm interested in what I'm doing. Okay? So we'll start with this equation. So this is a prelude. Okay? It's not part of the real lecture yet. And I would like for you to tell me what this equation is. By the way, feel free to ask any questions, say anything. If you feel like you know much better than I do, I'm sure you do. So just scream and tell me what you know. Okay, so who wants to give a try? Yeah.
A heat equation?
The heat equation. All right. Who else?
Diffusion equation.
The diffusion equation. Anything else? You had something else?
No, heat.
The heat equation?
Baby Fokker-Planck.
Sorry,
Baby Fokker-Planck.
the baby Fokker-Planck? Okay. You're all right.
But what are you considering here as a raw?
Well, I mean, yeah, I think that's part of the question as well.
The Lindblad equation.
Oh, the Lindblad equation.
Yes.
It's very... Okay, so, yes, you're all right, except you're not very precise. So what do I mean by this? When you say that this equation is a heat equation, what are you actually saying? Yeah? Have you heard this question before being asked? What are you actually saying when you say that this equation is a heat equation? So, as a physicist, when I say something is a heat equation, I'm not a physicist, but fortunately I live in the in-between, let me put it this way. I actually mean that there is a driving force, a driving mechanism to this equation. So when you think about the heat equation, what would be that driving force?
Energy transfer.
Sorry?
Heat transfer.
Heat transfer. What is the energy for heat?
Dirichlet.
The Dirichlet energy. So there is entropy, there is Dirichlet. So somehow we are all confused, right? Okay, so I'm going to write down the energy for heat. And it's going to look like this. This is heat. So when you say, or when I say, that this equation is a heat equation, what I actually mean is that there is a driving force behind that's driving this equation under some kind of mechanism. And this mechanism that relates the energy to an evolution is what I will call a kinetic relation. Okay? So there was also diffusion. What would be the driving force for diffusion? The entropy. Okay? So now, when I say that this is a gradient flow, this doesn't mean very much until I tell you what the driving forces are and what the kinetic relations are. Okay? So this is the philosophy of this lecture series. Yes, yes.
What did you call the first driving force?
The heat.
Just the heat
Yeah.
force they're on.
That's the heat force, yes, the temperature. It's, I mean, yeah, if you say, well, maybe usually you write this as that, right? So T for temperature. So where do these objects come from? So if I give you an equation like this, and I do not specify the energies nor the kinetic relation, then it's very hard to identify, well, what is this object even? By specifying the energies, I'm putting physics into the equation and saying, well, this equation is derived from a particular process. And this particular process is a process that you cannot see from this equation itself. So this is additional information that you have regarding this equation. Okay? And so this is, again, this is the philosophy of this lecture series. It's about gradient structures. Gradient structures are structures where you actually specify your driving energy, your kinetic relation, and what we will see later on is either what we call the Onsager operator or the dissipation potential. These are the driving mechanisms of your evolution. Is that clear? Are there any questions about this? No?
By the way, just a comment.
Yeah.
In somewhat of a reverse direction, one can think of, from a control's perspective, studying the long-term behavior of an equation like that, you like a Lyapunov function, strings or whatever, so that you can. So this can serve for that purpose as well.
Indeed. Yes. So these energies can serve as Lyapunov functions for mathematicians. So mathematicians, they like, but you can construct a lot of Lyapunov functions for one particular equation without knowing any physics underlying the equation. But there is a reason why making these specifications are very important. And throughout this lecture, so this lecture is 3 parts, and I think every day you will see the same thing happening, but in different settings. Okay? And all of these, the message here is that maybe you're not interested in the equation itself. Maybe you're interested in fluctuations away from the equations. When you're interested in fluctuations from the equations, then these structures play a significant role. Okay, but let's start from the basics. So many of you know what the gradient flow is, so this might be boring for you. I'm sorry. So one, gradient structures. Augusto wasn't lying when he said that it's not for short people. In finite dimension. Okay, so we start with an equation that looks like this. X, oh well, let me specify some things. I'm in the, so this frac X is going to be my state space, and I'm going to take frac X to be just RD. Okay, so we are in the flat space scenario, finite dimensions, flat RD. And I'm going to consider some force. My force is always some kind of calligraphic F that goes from RD to R. Sometimes it can take also the values plus infinity. But generally, assume for now F is a nice, smooth function. And then I can write this equation down. X dot is equal to minus the gradient of F of X. Okay? I think so far you know what this is. It's just time derivative of some curve. So X is now, you can think of X as a mapping from 0 plus infinity to RD. This is just a curve, and it's required to satisfy this ordinary differential equation, x dot equal minus gradient F of X. So what makes this, since you're all familiar with gradient flow, what makes this a gradient flow? Or what is the defining property of a gradient flow? Yes?
Oh, sorry, as I remember, so like we have a force that is like forming something. Like, I don't know if, and we want to minimize like and go to the...
Okay, so there's a property of that it's trying to minimize something, yes? Yeah?
Yeah, like as t goes to infinity, the x approaches to the argument of f if it's convex and lowers the continuous.
Yeah, okay. So, but the idea is that when you do this, you take the time derivative. So what, essentially just putting down on math what they said. You take the time derivative of F, the energy, along this equation. And then you end up with this gradient of F of X at T, more specific scalar product with the minus the gradient of F of X of T. Right, because I put x dot there, this is just the chain rule, and this is minus the modulus of f x of t squared. Okay, and this object is obviously non-positive, and therefore f is going to decay in time. And it's not only decaying in time, it's also decaying in time monotonically. Okay? And if the gradient of f is non-zero, you can see that there is some strictly smaller than 0. So it is trying to decrease until f hits a stationary point of f, by which the evolution just stops. All right, so this is nice and all. But what I want to do is I want to do something a little bit more. I want to give a variational perspective of this equation. This is an equation, pretty much like this equation right here. What I want to do now is try to relate this equation with a minimization problem. And a minimization problem on the space of trajectories. Okay? So how would you do this?
Maybe you
Yes.
can also make a comment here that related to what he's saying, or she was saying, I don't remember, that this is really the steepest descent, in the sense that if you try to take the derivative along any curve,
Yes.
you get always something bigger, right? So it's really the most negative you can be, in some sense.
Thank you. Yes, indeed. So this is also sometimes called the curve of maximal slope, or the curve of steepest descent. Any more questions so far? Okay, so, well, just continuing from these computations, we also see that we can write things slightly differently. This is the same as, if I write it in this notation for x dot, the negative of x dot square. Yes? So because these are the same, obviously that's the same as minus 1/2 of the gradient of f of xt, I should put my t here, squared minus 1/2 of x dot t squared. Okay, maybe I should have written something here. Yeah, apologies. I'm just going to write this down as f of xt, xt dot x dot t. Right, that's the chain rule. Applying the chain rule, I get that. But the gradient flow is telling me that this quantity is the same as that quantity. So now what does this remind you of? When you have A scalar product B, this is equal to negative of 1/2 of B squared minus 1/2 of, well, let's maybe do this instead. I'm going to change the sign of the negative. So remember, this is equal to that. I'm just going to shift the negative to this side. So I get 1/2 of A squared plus 1/2 of B squared is equal to minus AB. And maybe I'm also going to do this. It's the same thing. I put the minus B here. Yeah.
It's like a Lejeune-Venhill transform.
Yeah. Right? So this is Young's inequality, but with equality. So you know from Young's inequality that any for any vectors AB, you always get this. This is always true. And if you have equality, that tells you something about the relationship between A and B. Yes?
Oh, then B is subgradient.
Sorry?
Subgradient of. It's A subgradient of B.
A
Subgradient.
subgradient of B.
Yeah, they're saying like the subdifferential of the square.
Ah, the subdifferential. Okay, so yes. So in this case, fortunately, we just have A is equal to minus B. Okay, it's a simple way of saying because you have squares and everything is nice. Okay. All right. So, which means this is and only if. Yes. So which means if I have a gradient flow, and this is equal to that, then this is equivalent to saying, well, I can replace this, okay, because I can identify it. So if you look at this, my A was x dot, this guy. My B was the negative, my B was the gradient of f. And the fact that this is equal to this characterizes this equation, because it's if and only if. If this is true, then this is true, and vice versa. Okay? Is this clear? Okay, good. So therefore, if I were to just simply integrate this equation in time, look at I'm going to integrate it between any interval, then I will end up with f of x of t minus f of x of s plus the integral from s to t of 1/2 gradient of, I'm going to put here minus gradient of f of x of r squared plus 1/2 of x dot of r squared dr. This is 0. Just simply from this equation. Okay, it turns out that, okay, so maybe I'm going to give this a name. This is going to be defined as L of x, the curve, and an interval st. And this is what we call, people in the gradient flow community now call the energy dissipation functional, or the Lagrangian. And it turns out that if I have a solution of this equation, then this Lagrangian is 0 for every interval st, a subset of 0 and infinity. Okay? And vice versa, if this is 0 and the chain rule holds, which means I am allowed to go from here to here, then a 0 of the Lagrangian is going to give me back my solution. So these two pictures are equivalent under the assumption that the chain rule holds. That's equal to that. Is this clear? Okay. Now, even more, so we're not there yet with the full variational perspective, even more, because this inequality is always true. This means that this Lagrangian, because of the chain rule, so maybe let me assume that the chain rule holds, then I can write this as that as just the time dr of f of xr plus the rest, 1/2 of minus f of xr squared plus 1/2 of x dot of r squared dr. Well, we know that this quantity is nothing but so minus gradient of f of xr scalar product with x dot r, right? And we know that this quantity over here, because of Young's inequality, this quantity is always greater than that quantity. Therefore, this functional is always larger than 0.
You mean along any x, not necessarily.
That's true, not along any curve x. Not only the curve satisfying the equation. Okay? So this means that, in fact, the solution is also called the zero cost flow for this Lagrangian. Right? So now we have kind of 3 different ways of characterizing, characterizing a gradient flow, describing the curve. So the first one is these, hence these are equivalent. So the first one is that x dot is equal to minus the gradient of f of x. The second is that L of x st is 0 for all st. And the third is that x is an argmin of L of y st. Okay? So these are equivalent constructions. And it turns out that, you have a question?
I guess, like, if y is not the optimal x, is this finite if we do it? Oh no, wait, sorry.
Problem solved.
Problem solved. Okay. Yes.
All the solutions are parameterized by the initial state. In case, right?
Indeed. Yes, I always kind of, yes, I always leave out the initial state, but we always have to remember that there is an initial state and everything will depend on the initial state. You're right. Thank you so much. I've got lazy a little bit, right? But
is there a qualification on the intervals in part 3?
When you say qualification, what do you mean?
Quantification.
Quantification?
For all intervals.
Yes, for all. Yes, for all. Yeah. Sorry. Yes.
That's the qualification.
I see. Yes. This has to be true. Yes.
If you want to be picky, actually, it's enough to do s equals 0. In this case, at least, right? Or not?
In this case, if you want to be picky, also, you can also say t is infinity, s is 0. This is also fine. Yeah. Okay, so maybe I was not super clear on how we get back from here to the equation. So the point is the following. If x is a 0 of this, and if the chain rule holds, then this is true. This is all of this under the integral is equal to 0. Okay? But we know that this quantity is always greater than that quantity. Therefore, the integrand itself is non-negative. Its integral is 0, but the integrand is non-negative, and therefore the integrand should be 0. So if the integrands are 0 almost everywhere in time, then because of Young's inequality, we have this equivalent saying that A has to be equal to minus B, and therefore X has to be equal to minus gradient of F. And then you end up back here. This is how you go back. All right, so, and this is in fact the starting point. So this is all in finite dimension, but this is the starting point of describing general evolutions of gradient flow type, or generally gradient structures, on also very abstract spaces, including the Wasserstein gradient flow, or Otto gradient flow, and all the other things. Yes? All right. Okay, so you may ask the question, why bother going here? Why do I'm happy with the equation. You know, I can apply my Picard-Lindelöf theorem. Everything is fine. I get solutions. All good. So why do I want this formulation of this formulation? As I said before, it's easier to generalize the other formulations. But also interesting is that I'm from calculus of variations, so I like to minimize functionals. And more so is that I can do asymptotics. So if I have maybe now a family of these functionals, and imagine I put now an epsilon somewhere, and I'm looking to pass epsilon to 0, then calculus of variation tools are very handy because it tells me I can, you know, if I have gamma convergence, then everything is nice. Okay? So another thing is, as I mentioned earlier, these gradient structures, they make a difference on fluctuations. Now here we don't see very much because we've already specified, it's very hidden, that we've specified a gradient structure. I did not tell you which one, but in fact it's the quadratic one. But you will see more examples and you will maybe understand a little bit better what I mean. Yes?
So there's kind of like I'm just wondering a connection of this with a kind of more classical thermodynamic framework, which I kind of used to from like viscoelasticity, which doesn't really do gradient flow, but if you include like the energy dissipation, you know what I'm talking about.
Well, yes, for sure. So at this level we don't see it yet, but when I would say you will see maybe more in the next lecture, where I will talk about gradient structures in spaces of measures, and then we will see a little bit more with connections with thermodynamics and statistical mechanics. Maybe not so much viscoelasticity and stuff like this, but yes?
I have the impression that you try to say something and you don't say it. Because when you say gradient structure, are you saying, aren't you willing to write stuff without any gradient? Because to write a gradient, you need to have to specify the matrix. And the only thing that is well defined without a matrix would be the differential.
You will see in the, so this is, I would say maybe 1.1 Euclidean space. So here I don't need to specify so much my gradient structure. So I was saying it's quite hidden, because I've made a choice, an implicit choice, which is just
because we know what
the modulus.
Is.
Sorry?
Because we know what nabla is, right?
Exactly. So in fact, so the next one I will talk about in nonlinear geometries, and then suddenly we really have to be careful. And then I will have to make formal, I have to put down things properly on paper. Yes?
So I know the approach of discretizing to the implicit order scheme and then using the minimizing movement and convergence to continuous case. Is it related? Or?
Yes, of course. So now, yes, so if I look at this, and if I look at, this is my functional, and I'm minimizing this for any intervals. Of course, you can say, well, what happens when I start to discretize? If I want to really look for a minimizer, what do I do? You can say, well, let's take, for instance, a very, very small interval. Okay, and let's say S is 0, and T is epsilon, or tau. Tau is a good number because,
No, I love the fact you swap from epsilon to tau because you
tau
would
is
confuse out the...
Yeah, I'm sorry. Tau, right? Tau is the small time. Epsilon is a small something else, but okay, let's okay. So then what you do is you can always reparameterize in time. When you do this reparameterization in time, you will see that the x dot you will incur something. So if you just say r is equal to tau times s, and you are looking at the interval 0 to tau, indeed, so x dot, well, maybe I need to specify x tau of s. I define it as x of tau s. And if I were to take the time derivative, then this quantity will be after, so essentially x tau dot of s is going to be, what is this? Yes, so tau times x dot of tau of s, s. So x dot is going to be 1 over, so if I put my tau here, and I'm changing to s, then this is divided by tau. But because now r is equal to tau s, I have my s here, and I put my tau in the front. And because of the squared, I'm going to do this and put 2 tau and remove this tau. Now you see suddenly, this guy is kind of the kinetic part, the kinetic energy in a very, very small time. Whereas this, when I change this, I have my tau here. I have to change this to 0 and 1, because that's my s variable. This guy is going to be arbitrarily small. If tau is going to 0, essentially this guy is going to dominate. So up to order tau, this plus that is what's going to matter. And this is the minimizing movement scheme, or the time incremental, if you're familiar with the minimizing movement construction of solutions to this. Okay? Does that answer your question? The relationship? Yeah, okay. Any more questions? Yeah.
Just out of curiosity, I know that this is very like physical intuition, and but if we're looking at the Lagrangian or just by itself, we see that we're exactly using the fact that we have like Youngian inequality with the Lejeune transformers of each other. So can we, we know that like the Lejeune transform of x squared over 2 is the same one. So can we like start with a Lagrangian that has like, you do a sum of 2 Lejeune?
We will get there, yes.
Two of these, and there will be something else.
How much time do I have? 40 minutes, yeah? So maybe in 20 minutes you will see this, okay? All right, so let's, like I promised, let's start with, I can erase all of this. And then we're gonna work now on, so I'm gonna start by looking at Riemannian manifolds. My equation has to change in some meaningful sense. All right, so X is some kind of Riemannian manifold. F is going from now X to R plus. This is, I would say, generally nonlinear manifolds. So just for the mathematicians, or I don't know, like what I'm going to explain can be generalized really to also Banach manifolds and stuff like this. But I'm going to play it safe for now and just do. Okay, so this is our setting, but this equation is not meaningful, right? So if I'm in a nonlinear structure, I have to specify actually first of all, what I mean by x dot, and I have to specify what I mean by gradient. Okay, so generally, I'm going to put a little g here because this depends on the Riemannian tensor. So the Riemannian tensor is just some Riemannian tensor is a mapping that takes elements of the tangent space at x. So maybe I should put here g sub x, parameterized, of my space x cross to R plus. Okay, so this is given. Sorry. Yes, thank you.
It is definitely positive.
It's positive definite, yes. Sorry, it's without the plus because it's not a, okay, good. Thank you. So we have something like this. We're taking elements from the vector space, so the tangent space, and we're mapping it just to some real number. Okay, yes, and then associated to this, we also have a mapping that I'm going to denote it. Let me see if I can denote it like this. So this is G of x that maps element of the tangent space. So G of x is supposed to be symmetric, positive definite, maybe even coercive and stuff like this. And this will induce a linear map that maps elements of the tangent space to the cotangent space. And there is an inversion for this because G is coercive and this guy is invertible. So there is an inverse, which is what I will call the Onsager operator, because it was first kind of, I don't know, defined, but kind of used in evolutions by Onsager. This is G of x inverse, which maps cotangent vectors to tangent vectors. Okay, yeah.
I'm sorry, I'm just not very familiar with this. Can you give a short definition what is tangent space and this gradient with such?
A short definition of a tangent space.
And that's essentially the only definition. You take a curve and you try to differentiate them, and when it's a difference, whatever you get there, that you call tangent space. And that's all you know.
So you got an answer, or like? That's very nice. I mean, all I need to do is just erase the board, and then suddenly somebody answers the question. But it's fine? Okay, any more questions about?
What is the cotangent?
The dual.
But you also asked another question that maybe you're going to write, but that's important. What is the gradient? That's something that can be assumed.
Yes. So what I would define as a gradient here is, yeah, okay, let me, right, okay, so now what we know is x dot is an element of the tangent space. Okay? So which means whatever this object is, if I want to write equality here, it should better be an element of the tangent space. What always exists is, because f is a function from x, it has a differential. And the differential is, I would say, d of f acting on, at the point x, acting on v. Well, there are many ways to define this, but I'm going to define it in the following way. I'm going to take, what is it? The limit of tau to 0 of 1 over tau and f of gamma tau minus f of gamma 0, which is going to be x. Okay. With the curve satisfying, and this should be gamma with gamma of 0 is equal to x and gamma dot of 0 is equal to v. Okay, so for any curve that satisfies this, it turns out that this definition is invariant under the curves that I choose. So in the equivalence class, yes?
Is it like gamma of tau, not gamma of t?
Thank you. Yes. Right. So this is what jet lag is, this is doing to my brain. But okay. Yes. So we have this, and we can define this object. This object turns out to be a linear functional, because, so maybe I put here, I define it, because it acts on v. V is an element of tx of, I should make this more clear. This is an element of the tangent space. So it acts, that object acts on the tangent, an element of the tangent space, and turns out to be a linear action. And so this quantity is an element of tx star of x. Okay? So now I have, again, this quantity can be defined all the time. I just take curves and then I do this. So this is an element of the tangent, the cotangent space. Now what I need is somehow a map between, of course I'm hiding many other properties, people who are experts in all this type of stuff. Please forgive me, but hopefully this, I'm trying to reduce the number of notations so I can.
So cotangent space is the dual of tangent space.
Yes.
Okay.
Yes, it's the dual of tangent. Okay, so this is an element of the cotangent space, and I need a map that sends me from the cotangent space to a tangent space so I can make this equation meaningful. Okay, so what I'm going to do is I'm going to define, so actually not define, but in fact it's the same, everything is equivalent somehow. So define gradient g of f of x simply to be, so now I know because of my Onsager operator, I know how to take cotangent elements into tangent elements. Simply by k of x multiplied with d of f of x. Okay, and so this guy is an element of tx of, right? So which means this, bless you, so this equation is in fact an equation in tx of x. All right. Questions so far? Yes.
So, is it like an interesting case of considering pseudo-Riemannian tensor? Because you still have.
Yes, for sure. So if you, you can look at submanifolds, you can look at pseudo-Riemannian structures, you can look at many things, and you still have this type of. Except the inversion is not very clear, obviously, right? Because it's not invertible anymore, right? So. Sub-Riemannian structures are, you don't have invertibility, so you have to be very careful what you mean by, all right, this. Okay, all right, so now we are here, then we are safe, because in fact, when you see something like this, all it means is that we have something like this. X dot is minus k of x of d of f of x. So let me just say that this is the Onsager operator. And it maps cotangent vectors to tangent vectors. And it turns out that here we can play the same game as we did before. We take time derivative of f along this evolution, x of t. And then you have d of f of x of t acting, so just using this definition, acting on the tangent vector x dot at t. Okay. And then you use the dual structure that is associated to this stuff. And pretty much if you look, then you will see that this is the same as minus a half of x dot of t squared with respect to this this map G, but that is also the same as minus a half of the df of x of t. I'm skipping quite a number of steps here because of time, but k of xt. You are right. I don't know why is there 1/2. I'm sorry. Yes, because I wanted to write here 1/2. Yes. Now the 1/2 of x dot, exactly as before, right? G of xt minus 1/2 of d of f xt and k of xt. Okay, and then I can kind of play the same game and arrive with essentially the same conclusion as before, which means even in this setting, you can give a variational formulation to your evolution. Any questions? But what I'm going to do now is do an example, and maybe this will clear up a little bit of your question earlier. Okay, so an example is a very simple one, and it's the following. I have, so I'm x is equal to R2. Okay.
She wanted the spear. I'm joking.
But that's okay.
You can do polar coordinates.
Yes, exactly. No,
You're destroying my life. Okay, no, but okay. So I'm gonna stick to my R2, yeah, because it's Why didn't you ask Dario about the sphere? I mean, like. Okay, so let me see. What do I want? Yes, x dot is equal to v of x, and v of x is let me see, minus x1, x2 plus alpha x2 squared. So alpha is some positive number. Okay, so this is an equation. The question is it a gradient flow? Anyone? Yeah? So it's a gradient flow, but of what? So what is the gradient structure? Okay, let me now specify what I need for a gradient structure. In this setting, what I need for a gradient structure in the sense of these Onsager operators is a state space X, which I specified. I need an energy, F, and I need a family of Onsager operators, right, parameterized in X. So this gives me a gradient structure. So, which means I first need an energy. So what would an energy be?
I guess we have many options here, right?
Exactly. Give me one.
We can use the flat one, I guess, because it's curve-free, this thing. So again, we can use our two Euclidean, right?
Euclidean. Okay. So what would be the energy? So that would be the Onsager? Yeah. Flat? So you have to think of Onsager being kind of encoding some kind of geometry of the space. And the energy is something external, something I act onto the dynamics. So if I were to use the flat space, the Onsager operator would be identity. What would the corresponding energy be? One half of x1 squared plus one half of x2 squared plus alpha 3 x2 cube. Are we happy with this?
Yes.
No? We are happy with this? Okay, very good. Now, and then you can see directly that x dot is indeed equal to minus the gradient, the usual gradient, the flat gradient, because my k is identity of f. Can you give me another gradient structure? Funge, you cannot, but maybe somebody else can. So let me give you a hint. It's not the sphere.
Just add a constant.
Add a constant. For the energy. This is. I mean, you're cheating here. You're cheating here.
Can I ask the question?
Yes.
Can you move some part of the equation to the k?
That's the point.
Yeah. Right, and then make your f different.
Yes. So precisely. So let's take f to be simply 1/2 of x1 squared plus 1/2 of x2 squared. Okay? And I'm going to choose a k of x to be 1, 0, 0. And I'm going to do here 1. I need my 1. 1 plus alpha x2 squared. I need it to be symmetric and positive definite and stuff like that. Okay? So it turns out that if you take this energy with this Onsager operator, you also get, well, you get this. Minus k of x times d of f of x.
There's really the square there.
Probably no.
I wouldn't put the square in the k, but I know there should be positive definite. But
So wait, let me see. My energy is wrong then. I want it to be positive definite.
x2 times that.
Maybe then it's a cube.
Okay.
I'm sorry. Yeah. The sphere thing threw me off. I mean, like... Okay, so yes. Yeah, I do want it to be, because I want it to be invertible. Right? Okay. Unless you can always, no, you can't. Yeah, it has to be. Good. So these are two instances. Again, one equation, two grain structures. So when I say that something is a grain flow, I'm not really being very specific here. But saying what my grain structure is suddenly makes it specific. So then comes the question, maybe for a mathematician, you don't care whether you use this or this. For physicists, it turns out that it's very important, this or this. Why? Imagine you want to look at, like I was telling you before, that there is some parameter that you want to send to 0. Right? And maybe this parameter is the alpha. So on the one hand, you're sending the energy to 0. On the other hand, you're sending the geometric space to 0. You're changing the geometry of the underlying space. The energy stays the same, and the geometry changes. Of course, in this very finite dimensional R2 setting, maybe you don't see, maybe they commute very easily. But in many scenarios, this does not happen. So it's very important to first specify your grain structure before you actually do anything with it. Yes?
In the case of the gradient flow, I mean, if you make the same differential with a Newton step now, do you have this notion of energy also?
When you say Newton step, what do you mean?
Well, is dot equal the inverse of the Hessian times the gradient? So you replace steepest descent by Newton.
I see.
Do you have the same developments, or?
In some sense, you are changing the local geometry, yes. Right? You're choosing, well, of course it's not so, because your k is not independent of your f if you use the Newton. Because you say you're going to multiply with a Hessian, so this is kind of you're doing some kind of a conditioning, right? But this Hessian depends on the energy itself. So here it's a little bit different because you want to kind of separate the energy from the geometry of where you're evolving. So here, this object here, this k, is completely independent of the f. Every time I change my f, I'm not going to change k. It's going to stay the same. Right? And this is in fact a kind of thing that we want, because if you create a grain structure where let me put it this way, maybe let me use the term metric for now. If you create a grain structure for which the metric depends on the energy, then there may be something weird happening. Every time I change my energy, suddenly I have to change my space, my metric space. Right? And this is what happens, I think, in the Newton step, because your Hessian is going to be the Hessian of f. Okay, yeah.
I'm just like trying to go back and recall some of the things. So here K or G, they're responsible for the geometry.
Yes.
Like and the F is just like the potential. So here in the first example, like let's say we have the usual geometry, or like in the distance is like the the length in between the points, or?
Yeah, this is just straight, flat. Yeah.
Okay, and in the second one, how? Like, I'm just trying to, like, let's say, look at the metric. So in the metric, in the first space is like just the usual square like metric, and here, how do we define the metric? Like, can we write it?
Yeah,
somehow?
yes, it's given by the k.
Yeah, but
so,
like, let's say, what is the distance between 2 points?
Precisely, you can write it down because k. Remember, k is the inverse of g, and g is precisely coming from that object right there. So, in fact, what I can do is I can do the following. I can invert this guy. So the inverse of this guy is quite easy. G of x is just 1, 0, 0, 1 over 1 plus alpha x2 squared. Okay? Now with this g, I can write down, in fact, this g of little x of u and v. Let's say u and v are just tangent vectors. This is going to be equal to the scalar product of g of x applied to u. And, okay, so this is not the scalar product, this is the duality pairing. It's not scalar product. U and v, where u is a tangent vector, g maps tangent vectors to cotangent vector, and then I act on the tangent vector. So in other words, I can also write it like this, acting on this. Okay? So, but this gives me a way to describe something like a metric. And we know that the length of any curve, or essentially the geodesic length, is given by the integral of gx of gamma dot, taking the square root of r dr, and also r here, right? This is the length of gamma. Okay, so what you can say, well, if I fix 2 points, I can define my length functional. The minimizer of this length functional will be the curve that goes fastest from A to B under this geometry. So this guy alone specifies pretty much the geometric structure of your underlying space.
So like the distance between like 2 points like x and y would be like the curve, like the length of the gamma that goes from x to y.
Arc length of this, yes.
The minimum.
The minimum, yes, the geodesic amount. And in this case, it is the geodesic, so which means it's also constant speed. Okay, yes.
It's a nice observation. Like here, the geodesics for both the spaces are different, but the curves that minimizes your functionals will be the same.
Yes, so the curve that minimizes the full Lagrangian, the full Lagrangian is the same. The zero cost flow is the same. Okay? But the geometries are completely different. I have 2 completely different linear functionals. And so this means that if I'm really looking in physics, and the physics is telling me, well, your geometry of the space is actually different. It's not the flat one. It's a different one, maybe caused by friction. Then if I'm interested in deviations away from the zero cost flow, suddenly the numbers change because I have a completely different functional. I mean, take for instance a functional that looks like this and a functional that looks like this. These are 2 functionals. The zero cost flow, this is 0, is exactly the same, but how I deviate from it will change completely. So if you're doing measurements, you're trying to understand like how far you are, in fact, from seeing something that is common, then these functionals play a huge role. Any more questions? Let me see what else I have. Okay, so now we can generalize very quickly away from, so this was the computation that I have done, and if you're familiar with all this Legendre, Fenchel duality stuff, then you can also see that everything that I've done here can be generalized to non-quadratic. Right? So this is squares. So non-linear geometries. well, maybe not non-linear, but non-quadratic geometries. So what we can do, pretty much as Natalia already mentioned, is replace these quantities with something more general. So we consider the functionals, or what I will call the dissipation, dual dissipation, potentials. So I'm going to denote it by R and R star, where R is a mapping from X cross tangent X to, here I would say R plus this time, okay? And R star is going to be the dual. And such that for which R of X comma dot and R of X, so R star comma dot, is a dual pair, or maybe more specifically, Legendre-Fenchel dual pair. So which means they are conjugate of each other. Are you familiar with this? No? Yes? Yeah?
I mean,
Sorry?
it's a good idea to just give an example, like exponential and
I don't know if...
x log x.
X
minus
over
1.
E and so it just generalize Young.
Generalize Young maybe, so... Okay, so...
By the definition, I guess.
Sorry?
You write the
I can
definition
write the
of the
definition down and maybe give some examples. So, say just let's take psi. Psi is a functional, say, from X to R. Is let this be, so this guy can be, in fact, a Banach space if you want. Yes?
Right, and we need that here, it comes from the tangent space?
No, so this is a general functional on just a Legendre duality. So X is a Banach space. We can take a Banach space. Let this functional be, so I'm going to assume directly that's convex and semi-continuous, lower semi-continuous. Then it's Legendre-Fenchel dual, or conjugate, maybe conjugate, is given by psi star of psi is equal to the sup of some duality pairing between psi and what do I want to call it? Let's call it S, sorry, minus psi of S. So the supremum is taken over S in this case. Okay, so this turns out to be a nice object. It's also, again, going to be convex and lower semi-continuous. Of course, you can ask for a lot of other properties like growth conditions and stuff like this. But okay, there is a whole series of equivalences you can write down for this type of objects. One of the nice things is that you see here is a sup, which means, so just a remark, maybe a couple of them. So the first remark is that for any pair S psi, this is in X, I have to define here psi is an element of X dual cross X star. we have that, yeah, again, because this is the soup, psi star of psi and psi of S plus, this is always greater than psi of S. Yeah, this is what we call so the Fenchel-Young inequality. And you have equivalences, maybe two. The following are equivalent. So one is that yeah, I have to, okay, I'm just going to write it down. And if you don't know what this means, then you have some homework to do, okay? So psi is an element of the subdifferential of psi at S. And two, that equality holds. Okay? Psi of S plus psi star of psi is equal to psi of S. And three, the reverse of this, S is in the subdifferential of the dual of psi. Okay? So these are equivalent, well, assuming that X is, yeah, I will assume that X is now separable and reflexive and stuff like this. Yeah? So X is separable and reflexive. And then you have these equivalences. And these equivalences, pretty much like before, how we go from equations to just the functional, this is what gives this, right?
So when the functions are defined over R, like when it's mapped to R, convexity is equivalent to continuity, right? So you have to, it's extended functions or it's just function?
So, well, convex function, it's continuous in its domain, but obviously, well, okay, now I yes, because it's in R, yes, it's continuous everywhere. You're right. Because the domain is pretty much all of R. I mean.
So you include infinity, then.
So if generally you can include infinity, plus infinity, and then in this.
You have to specify that it is proper as well, right?
Yeah, yes, because otherwise there's nothing to talk about. Yeah. Okay. So what should I erase? Maybe here. Okay, so what we have here is then, because of this, we can play this game. So we're going to assume that these guys are dual pairs, which means in this situation, for each x, you can think of this as the psi, but for this variable, for the next variable. Okay, so the tangent space is a linear space, maybe a Banach space, right? Then all of this applies. So for each little x, we require that R star is equal to R. Okay? And R star is equal to that guy. So we really have a dual pair. And in this situation, we can generalize very quickly because we can consider the energy, maybe I start here, dissipation functional, which depends on this L. So L depends on the pair of X and ST. I'm going to define it as pretty much as before, except now I have R of X of little r, X dot of little r, plus R star of X R and minus d of f of x of r dr plus the difference So pretty much like before, nothing has changed. And you can see you can play exactly the same game. So the zero cost flow for this, right? So if L x st is equal to 0, then, well, maybe not if, but I would say this is if and only if. So assuming we have the chain rule, this guy is equal to the integral from s to t of d of dr of f of xr dr. And we get again st of d of f of xr, acting on x dot of r dr. And we use essentially the Fenchel-Young inequality to say that these two objects are always going to be greater than this object. So if it is 0, then the integrand, so if I pull this inside the integral is non-negative. But because the integral is 0, the integrand is non-negative for almost every time, which means this equality is true, and then you can choose either to take this or that. So this will be your equation. Yeah? So you end up with an equation. Vice versa, if you start with an equation, then you get this. So let me write down the equation, so which means that x minus, I would say, which one do I like? I like that one. So x dot, it's in the subdifferential of r star of x of t, so x dot of t, x of t, and minus df of x t. So this is the equation. This holds, of course, for almost every t. Okay. Yes, and in the same way, you have, again, the variational principle. The minimizer of this is... Oh, yes. Online. Oh, really? Okay. Yes, question? I'm sorry.
Yes. Oh, I hear myself. Wait. Okay, so I just wanted to say, so one remark and one question. So if I understand correctly, what you are using here essentially is the fact that the Fenchel-Young inequality is a generalization of the Young inequality, yes, and the fact that the Fenchel transform of the half of the square norm is equal to itself, right? So
Yes.
that's why what you write here is a generalization of what you wrote earlier, right?
Indeed. Is there a question? Yes. Your comment was correct, yes.
Okay, and my second question is
Now I think it got muted. I think it got muted now. Yeah.
There were. Okay.
He can
Yeah, maybe he can try again later. Yes.
Yeah, but
sorry. Yeah, so my question is, so what we are doing now is not quadratic, right?
Indeed.
But to what extent what we did in the Riemannian case was quadratic?
To what extent?
Yes. Why this section now is non-quadratic, whereas what we did in the, I mean, how do you classify what we did in the Riemannian space? Was it quadratic or not?
It is quadratic, so I can write down the dissipation potential. So the dissipation potential, R of X and S, is nothing but the S, oh, well, I would say G of X, S, and S. 1/2. Thank you. Yes. Adil, does this make sense?
Okay, I get it. Okay.
Yeah, okay.
Thanks.
All right. Yes.
yeah, but the problem with Fenchel is that in general, if you know that R is convex, you don't have access to R star in general. Explicitly, I mean. It's very rare. For the quadratic is a very special case.
But there are many cases where you have explicit...
But corresponding to physical application, I am not sure, right?
Yes, there is. So I will show you precisely. tomorrow where we see really completely non-homogeneous, non-P homogeneous, something that's really exponential, where you have the dual and then it's coming from physics. Or I would say it's coming from statistical mechanics. Yes?
Yeah, I have a question. What is the meaning of g of x acting on S? So g of x is the element from cotangent space. This is like dot product of elements from cotangent.
Okay, so this is the duality pairing. Maybe I should write like this. So this S is a vector, a tangent vector. G applied to tangent vector becomes a cotangent vector, and then I apply it to S again. Yeah, so it's nicer to write it like a, pretty much you can think of it like a matrix. Yeah. Yeah, if you want, this is nothing but Gx of S and S. That's the same thing. Yes?
Just a comment, if I remember correctly, like in viscoelasticity, I think this would kind of fit the framework where R, like a typical R, would look like something like the time derivative of the deformation gradient squared, possibly more complicated.
Yeah, okay.
And then the energy would be like normal kinetic energy and the hyperelastic.
So yes, I think in general I want to agree with you. Yes, when it's maybe viscoelastic, then it becomes very difficult because you would not expect something that is more one homogeneous than two homogeneous. Especially when you want to talk about just sudden change, because like if you have, so I mean not viscoelastic, maybe more like plastic deformations. Then you have this. Because you have situations when you go from something that's elastic, suddenly you go into a region where you cannot go back. And you need to track this not from the energy, but in fact from the dissipation potential itself. Yes. So maybe just let me say the notation R is made very, intentionally, because, yes. Very intentionally, because this means Reibung, which is German for friction. Friction, force, if friction has a force. But okay. Yes?
Can you write down what is R star in the Riemannian case, please?
Does that make sense?
Thanks.
Yeah?
Yeah,
okay.
It makes sense.
Yeah.
Hi, can I ask-
Yes.
Do you strictly need a Riemannian manifold to define the concept of a gradient structure, or can you get away with it?
So all of this does not need Riemannian manifolds. So Riemannian is kind of the fact that you have something like this. And this does not have that. So Riemannian structures are quadratic in, sorry. You need a differential structure, yes, but not necessarily a Riemannian structure. You need to be able to define the D, the differential of the F. That's what you need.
So do you strictly need this K, or as in this Onsager operator, do you have to define it, or?
If I expect so this is the part of the modeling, right? If I expect my system to be quadratic, then specifying K or specifying G, which is equivalent, would suffice, because you expect quadratic objects. But there are many objects in nature that are non-quadratic. In which case, you don't specify the Onsager operator, because in this R formulation, you don't see the Onsager operator. The Onsager, well, it's not really an Onsager. Okay, so what it does is, what does the Onsager operator do? It maps cotangent vectors to tangent vectors. And this is something that you can do by this duality stuff. If psi is super nice, if psi is differentiable, then psi is the gradient, or essentially psi prime of S, if you want. Maybe more like this, and the other way around. And in fact, you can invert. So because psi is, say, assume that psi is strictly convex or whatever, right? Then you can invert. So you can go from tangent to cotangent and vice versa. So this is kind of the mapping that brings you from the tangent to the cotangent and back without Onsager.
But why do we really need this non-quadratic case? Like,
why do we need the non-quadratic? I will show you tomorrow. Yes.
Well, I would also say for stuff like viscoelasticity, but I realized another. Sorry if I'm kind of talking myself here, but in the viscoelasticity theory, the energy includes kinetic energy, which has a time derivative as well. And so I don't know if you've looked at that, but there's actually work that the variational methods work really well, despite seeming like they might not because of this derivative.
Yeah. Okay. So you're referring to works from whom specifically?
I can try to send you that later.
Sorry?
I don't remember.
Okay.
I think like Czech authors.
I have one more question.
Yes.
Is this too general?
Is this too general?
Yeah.
No. We need this.
I mean, are you not, if you take arbitrary spaces, infinite dimensional, arbitrary tangent spaces, are you not going into some category where solutions are not so meaningful anymore?
No, not really. So I personally, it would be nice. So I've not done, we've worked on, say, jump processes. You will see tomorrow. Well, I will not talk about it tomorrow, but essentially you can talk about jump processes, which are going to be gradient flows. I don't specify the gradient structure, but these are gradient flows, and they can jump on very abstract spaces, essentially Borel spaces, standard Borel spaces, which would include many type of spaces. And why is this so interesting, at least for me, is because I would like to study jump processes on path spaces.
On quantum path spaces?
Hopefully someday, yes. Maybe within the 3 months, yes. Yes, hopefully. But or even on configuration space or on Fock spaces. So in fact, there are works that I've worked on where we looked at birth and death dynamics. And we asked the question, is birth and death a gradient flow? Because when you're birthing, it's not so trivial anymore because you're going from one layer of the Fock space to another layer of the Fock space. Then you have to ask the question, okay, is it still a gradient flow? Under which condition it is still a gradient flow? And things like this. You can do asymptotic limits and derive equations preserving the gradient structure. So this is something that's I will not touch at all in this lecture series, but if you have a gradient structure and you pass to some limit, there is a chance that you can induce a gradient structure in the limit.
If I may be so bold, but I would really have a work to do on this birth process in the commutative and non-commutative case.
Me too. I would, we really like.
Isn't that the purpose of all tutorials, that we identify something?
No, yes. So I think, especially on the level of the number operators and stuff, this is super cool.
We have discovered this birth process are super interesting as well. So.
Okay. Very good. So we have a lot to do. All right. In view of time, I think we should. I'm done, right?
Can I just make?
I have 5 minutes.
I think so. No.
It's.
Sorry.
Yeah, minus 10.
Minus 10.
So tomorrow's lecture I will deduct, right? It's fine. Lorenzo, no more questions from you. Okay. All right. Thank you very much. Yeah.